went through the wrong proof. Okay, this is actually of the form of a matrix A, or let me call it a matrix A, is of the form of a matrix G minus its Hermitian transpose. So a matrix of this kind has to be Hermitian. Okay, it has to be Hermitian. So you just have to prove that this is the conjugate transpose of that. And many of you started to plug in reciprocity relationship and all kinds of things, expansions in terms of eigenfunctions. That's not necessary. This thing itself is Hermitian. So let's see how we can prove that. So I went through some very simple analogy yesterday. Hopefully this can help you understand this a lot better. Let's assume that if we have just linear algebra, that we have a scalar C, which is an inner product between a vector and a matrix and a vector. And I can rewrite this very simply as Bj, Bj, Bij, just actually very simple-minded exchanging of the order of this thing. I can also change the indices to make this into Bi, Bji, Aj. Okay? And then I can use vector notation now to rewrite this. I can write this as A transpose dot B dot B. And the second part, I can also use matrix notation to write this. Okay? And this is just a transpose of that. And this is definition of what the transpose is. So I immediately arrive at the fact that the element, the ij element of this thing is Bji. Okay, this we know in standard linear algebra. What happens if we have complex conjugation then? Things gets a little bit more complicated. You can go through the same thing, Ai, Bij. Let's assume that Ai and Bj are real so that we don't have to take complex conjugation with them. But this proof is general. Okay? You just take complex conjugation of this left-hand side. This must be true. Let's assume that Ai and Bj are real. And the second part will become Bj, Bij, Ai. Okay? And then I can rewrite this as equal to Bi, Bji star Aj. Okay? I can use matrix notation now and write the first part as, since A is a real vector, okay, this is just the complex conjugation of the matrix B dot with Bj. Okay? And then this can be written as no J here, sorry. B transpose dot Hermitian conjugate transpose of A. Okay? So from this very simple linear algebra, you can see that the ij element of this conjugate transpose is Bji, complex conjugation. This we know, okay, this we all know from our course in linear algebra. I think what confuses most of you is what happens if we have a mixture of tensors and Hilbert space vectors together. We have three vectors and diodes together. Then what we have is something analogous to this. If C is a scalar number that is due to the inner product of Ai, this is a three vector. Okay, this is a diode. And then this is another three vector. What happens if we have C that instead of being formed from scalar numbers are formed from vectors and diodes? Okay? And then I can go through the same thing as the scalar case, write this as Bj transpose dot Bij transpose dot AI, and then this can be also written as just by changing these dummy variables as Bi transpose dot Bji transpose dot Aj. Okay, just changing of dummy variables. Now if I use a kind of super vector notation, because these are not these simple vectors, but a super vector notation, that I stack this into a vector and use a blackboard ball to denote this. I stack this into a matrix. I use a blackboard ball to denote this. Okay, I can write this as this now. And then this part, the second part would be the blackboard ball transpose with this transpose with A. Okay, and from this, clearly, this is a blackboard ball A. You can see that this is a super matrix stacking all these 3 by 3 matrices together. The Ij component of this is equal to Bji transpose. Okay, you can see that this is true. This Ij element must be equal to this element over there. Just like how we equate this one. Now you go to the complex case. Complex case is what you often deal with. Bij. Okay. Assume A and B are real again, so you need to only take the conjugate transpose of this. Okay. And then again I swap them around, take the transpose of them. Bij conjugate transpose dot AI. Okay. And then I can change the indices and rewrite this as Bi transpose dot Bij transpose dot Aj. Okay, I can rewrite them as such. And then I can use super bold-face notation or the blackboard bold notation to rewrite this as C conjugation is A blackboard bold representing these vectors all stacked up together. This blackboard bold represent these matrices all stacked up together. And this blackboard bold to represent these vectors all stacked up together. And then the second part I can also write as a blackboard bold transpose dot with this dot with A. Okay, and from this clearly you can see that if I have this super matrix, this should be conjugate transpose, sorry. This should be conjugate transpose. And if it takes its Ij element, it's equal to B. Let me see, this one should be conjugate transpose, sorry. B Ji, I think this should be Ji. Bji conjugate transpose. Okay? So if you see what this exercise tells you is that if I have an operator, say B, if I find its conjugate transpose, it's taking the submatrices, conjugate transpose the tensor element, these are the tensor elements, and then swap the indices. This is how I find the conjugate transpose of this. Okay? So if you extend it to the dialectic Green's function now, so if I have, say if I think of the dialectic Green's function as a super operator in Hilbert space, I want to find its conjugate transpose. What is it? Okay. I know the coordinate representation of this. This is just equal to R prime. What is the coordinate representation of this? You find this coordinate representation by taking, if I use direct notation, as been taking this with this one. Okay, if I use direct notation, I'll find this matrix element using that one. This one, if I use direct notation to find its coordinate representation, according to this rule, okay, would be equal to G conjugate transpose R prime R. You conjugate transpose the tensor element, you swap the indices, and then you swap R and R prime. I think some of you thought that this was a typo. Some of you thought that this was a typo. It was not a typo. It was meant to be that way. Okay, so this is the Hermitian conjugate of this one. And because of this, this is automatically Hermitian. And you don't have to go through the long proof that you went through. A lot of you went through very long proofs. Okay, it was meant to be a very simple problem. Okay? Any questions regarding that? So problem 3, I think most of you get it. So I won't go through problem 3. Problem 4, part C, none of you got it. None of you got problem C, part 4. Now let me go through that in some detailed review then. Okay. Let's see what that means. So, if I have a wave equation, and if I want to study a scattering problem, say K0 here and K1 over here, okay, and then find the scattering solution, then I can write the general solution outside. From chapter 1 of the book, that the general solution outside is A0 prime, spherical Bessel function, A0 L, ENN, cosine of theta, e to the IMC, right? Plus the reflected component, HL1 K0R. I actually don't need you to derive this, I just want you to say where the other resonances will come from. Okay, I don't want you to derive it, but maybe the derivation will be more convincing that there are other resonances existing as well. Okay, this is a solution outside the sphere. Inside the sphere, it should be something like this, a standing wave. Okay. Let's assume that we are in the long wavelength limit. So K0 tends to 0, K1 tends to 0. Then I can make use of what I know about Bessel functions. JLX is x to the L. HL1x would be x to the minus L plus 1. You can look up from chapter 1 of my book, or you can look this up from Abramowitz and Staker. Okay, these are the behavior of the Hankel function when x tends to 0, the Bessel function and Hankel function, and how they behave. You can look them up in 10 books. So I seek a quasi-static or long wavelength version of this solution. Then when omega tends to 0, then phi 0, which is outside the sphere, can be written as A0 RL YLM theta phi. Let me call this YLM, plus a reflected component B0 R minus L plus 1 YLN theta phi. Okay, this is outside the sphere. And inside the sphere, I have phi1 is equal to A1 RL YLN theta phi. Everybody agrees? I just let the frequency drop and take out the principal variation of this R according to this formula. And these are the static solutions outside and inside the sphere. Next thing I do is to match boundary conditions. Boundary conditions should be tangential. No, actually, potential continuous and normal derivative of the potential be continuous after multiplying by epsilon, proper epsilon. So if I match the boundary condition that this equals that on the surface of the sphere, which I assume to have a radius a, then I got the first equation, a0, al plus b0, a minus l plus 1 is equal to a1, al. Okay, I just match this to that at the surface. The y's cancels because of phase matching conditions. Okay? And then I impose the other boundary condition, which is epsilon 0, ddr, phi 0, and r equals a, must be epsilon 1, ddr, phi 1, and r equal a. Okay, this is normal flux is continuous boundary condition. And then I get the other formula, the other boundary condition, the other equation. And what I get is that from this I get this other equation as my thing, epsilon naught a0 l a l minus 1. You differentiate this once, you get l times r l minus 1 divided in l. R equals a, you get this, and then the second one you get a negative sign. Okay, so you get a negative sign, you get L plus 1, a minus L plus 2, B naught. That is the second term. And then this must be equal to epsilon 1, A1, A minus 1. Okay? So two equations, two unknowns. This equation, this unknown. So I make the right hand side look like each other and equate. I make the right hand side of these two equations, 1, equation 2, look like each other and equate. So I will have to multiply this whole equation by epsilon 1 L. Okay, then the right hand side will be equal to each other. Am I right? A, right? Very good. Multiply by A as well. A inverse, am I right? If I multiply epsilon 1 L times A inverse, then the right hand side will be equal to each other. Then I can equate the left hand side. I will get this equation for the left hand side. Epsilon 1 L A0 A L minus 1 plus B0 A L plus 2, okay, must be equal to L plus 2 B naught, right? I will get left hand side equals right hand side, I will have that. Now I solve for my B, solve for my B naught. B naught turns out to be A0, A2L plus 1, L epsilon naught minus epsilon 1 divided by epsilon 1 L plus L plus 1 epsilon naught. Okay? You can do that in your head and see that. So you see how this differs from the dipole one, right? Dipole one, what is L for dipole? 1, right? L for dipole is 1, then this is epsilon 1 plus 2 epsilon naught. And you get a resonance frequency by setting this to 0. You get the resonance condition because this can be negative for subharmonic nanoparticles. And because of the different multipole components you're considering, you will get different resonance. So if you sweep the frequency you should see the dipole resonances and also the quadrupole resonances, the octupole resonances, and the other resonances as you sweep the frequencies. And as some of you noticed in Matu Hui's literature review seminar, he was scanning magneto nanoparticles. He saw all these resonances. But it was still in the long wavelength filament. And the reason why you have the other resonances is because you excite the other multipole components. Okay? So if you assume that epsilon 1 is a coplasma, okay, then you actually get this very simple formula. And you get that the resonance frequency of coplasma is just a plasma frequency times 2L plus 1. Okay. This is very nice formula for the case of a dipole. It would be 1/3, right? 1/3. And you see a whole bunch of resonance frequency. Even in the long wavelength filament, even when the wavelength is much longer than the size of the particles, you will still see these other resonances. Okay, I'm done with reviewing the exam problems. I actually prepared something from Uiuc. If you want me to go through them, I can go through them quickly with you. This is light emission and optical interaction in nanoscale environments. Very tricky derivations in some of them. Okay, maybe you can learn about the tricky derivations. That is good enough for you to learn. Okay. So are there any questions regarding this? If not, go to Novotny and talk about optical interaction in nanoscale environment for the last part of the course. Actually, this has also been reported in the literature. I thought I remember seeing this somewhere, but I couldn't find the proper reference for it. So I googled the internet and came up with one that has this formula. And let me give you the reference. SPIE 2005. And it's by KOLWS, or maybe WAS. And ADERKAE Choba. Okay, proceeding of SPIE, volume 5849. Okay, it's in there. Okay, another thing I noticed very interestingly in your exam is that some of you use Wikipedia to look for your answers, and those are wrong, especially the one on radar cross-section. What was it, Aditya, that you got from Wikipedia on radar cross-section? What did Wikipedia say?
Not radar cross-section, the optical theorem.
Well, somebody got something from Wikipedia on radar cross-section. It was kind of funny results. It's you, right? Somebody have to come. You have to admit, get something from Wikipedia. Did you, Ken?
No.
No?
I always use Wikipedia.
So what was
So it could be me, I don't know.
Okay. It says that the radar cross-section is the cross-section of a perfectly conducting sphere.
Oh, I did not say that.
Or something.
I said that.
You say that?
Yeah.
Oh, okay, that's wrong, right? That cannot be correct. Did I take points off?
Yeah. 3 points.
So it's not correct, okay? But you think about it. Radar cross-section is not that thing that Wikipedia say. Okay? So don't rely always on Wikipedia. I think somebody ought to go in there and correct the answer in Wikipedia. So let's talk about light interaction with molecules in a nanoscale environment. So when you're dealing with nanoscale environment, then the granularity of the environment becomes important. So we have to worry about granular effect. So granularity becomes important. And then in general, you can replace charges not as a continuous charge, but as a sum of point charges, which can be represented by the other function at each location. Okay? And then if you have any current, the current can be due to moving charges, so they can be due to the velocity. I'll send you this document later on when I'm through with this course. Okay? If these moving charges are moving around, they give rise to current. Current is given by flux. Okay? What is more interesting is that, so let me draw a picture from the book. So I have this granular molecules or charges that I'm dealing with, and then these charges might be associated with atoms, and this is Rn. In general, I'm interested in the field at the point R. Okay? And it turns out that the current J can be written as dP dt as we know it. This is called a polarization current. And also can be written as curl of M. If you have any magnetization in your medium, you also give rise to a sort of current. That current is given by curl of M. Does everybody know this? Right? Because there's no truly magnetic monopole in this world. Magnetizations are due to circulating current. If you take the magnetization current, you get back current itself. And you can also see this from Maxwell's equation. Curl of E, I omega mu H, curl of H is I omega epsilon E plus J. Say if I have a magnetization, I can rewrite this as being equal to, well, how do I rewrite this? It would be curl of E is I omega mu. Let me try with H plus M first. Okay, let me try with this one. And then the second equation I can write with curl of H plus M is equal to I omega epsilon E plus J. And then I can take the M on the other side and write curl of H is equal to epsilon E. If I put a minus sign here, then things come out right. J plus curl of M. So the curl of M does seem to give rise to a kind of current if you regroup the magnetization with the current group. Okay, so if you have any magnetization, okay, then you can actually, I think that's correct. You can regroup it and then it looks like a current in Maxwell's equation. I hope I did this right. If I don't do it right, then you can go and think about it. Okay, so magnetizations can be grouped and regrouped and can be thought of as a current. And you take the curl of magnetization, you get current. So, but we know that charge is divergence of P. Okay, that we know from Maxwell's equation. This is P is something like epsilon times E. So if you take the divergence of P, you get charge. Okay, or minus the divergence of something. Okay, I think this is correct, right? What?
Kappa.
Kappa, right? Is it kappa?
That's, yeah, I guess it means something
Maybe some chi. Maybe some chi.
Maybe something like that. Usually written as, yeah, something like this, right? So you take the divergence of P, you get charge. So, but there's something very interesting. It says that if PR is equal to this, if PR equals that, and you plug this into here, you get this to be that. It's not obvious that it's true, but it's true. Okay? And then it also says that, Novotny also says that if MR is defined to be equal to this, like kind of like a moment times the velocity is like the angular velocity or angular momentum, and then if you multiply this by that, and if you plug this into here, this equation over here, you get the current back also. Okay, it's not obvious, but it's true. Okay, it's not obvious, but it's true. So I look at the references. The references go to CP, Craig, and through something. You remember the second author's name is the Tamil name, quite long.
Oh, yeah.
Rananam or something like that.
Yeah, I got it.
Okay, a very long Tamil name. I couldn't really remember. Okay, so plus something. Okay, very long Tamil name. So the derivation is found in there. Okay, in order to prove that this is true, I have to establish this identity. And this book changes notation on me again. Okay, so R sub n get changed to Q. Q is the location of the charge. And if I can prove this, so our library doesn't have that book.
It has it.
It has it? Okay. Can you get a hard copy from me? Okay, the S has been replaced by lambda. So you can prove this identity. First, you have to establish this identity, which is not easy to establish. The Q are actually the R sub n over there in the previous equation of Novotny. Okay? I think this alpha should not be there, but it's in this note anyhow. So you can prove this identity, then you have this fact proven, which is that this and this when plugged into here will give this thing, and then this when plugged into here will give you the charges. Okay, let's try to prove this identity. And in order to prove this identity, we need to use initial notation, index notation, which is also called Einstein notation. It comes in handy. So it's a good time to learn something about index notation. So let's look at the I component of this. I component of this, and this should be a vector, sorry. It should be a vector. So I can look at the I component of this equation on the right-hand side. And let's look at the I component on the first term on the right-hand side. I can write d dt, the I component of this is Q minus R I, okay, plus this very complicated integral, the lambda of the delta functions, okay. And if I differentiate this with respect to t, r's are fixed points, okay, r's are the fixed points, like in the case of CP crate, r is the origin of the group of charges. So it can be 0 in this picture over here. Okay, it's 0 in this picture over here in Novotny and Heck. So if I differentiate this first, I have to differentiate this term. Okay, so I get the I component of this differentiated with respect to time times this integral 0 to 1 delta d lambda okay, plus the second term, which is the differentiation of what is inside. But how do I differentiate things that are inside? The only thing that could be changing with time is this one over here. Inside, the location of the molecule. Q is the location of those charges. You can be moving with respect to time. And if you differentiate with respect to the inside, you get this one, okay? You get a term that looks like this: Q minus R I Q J dot. Okay, Qj, and then integral 0 to 1, then lambda sum of j delta r minus r minus lambda q minus r d lambda. So the first term is easy to understand. You just differentiate this one, you get q dot. But when you differentiate the inside, the innards of this, you get this one. How do we get that? And it's harder to understand. And in order to read initial notation, when you see two j's together, what does it mean? Sum over all j's, right? And in this case, the j's refers to 1, 2, 3. The 1, 2, and 3 components of the three vectors. So there's an implied summation over here. So this is actually what we call a dot product. When you have j components sum with the j component, that's a dot product. So how do we get this? This is actually quite common in fluid dynamics. If you read literature in fluid dynamics, then if you take the autoderivative of a function of Q, let's say it's changing with respect to time,